All right, so kind of picking up where we left off with this F-test. And so again, back to our hypotheses, we're testing to see whether our slope coefficient is different than zero. In other words, we're testing to see if there's an association between our explanatory and our response. You'll end up practicing this on the golf example in the accompanying handout. And so our F statistic, if our alternative hypothesis was true, you could kind of take a second to think about whether that is going to be small or large. And to determine that, we want to go back to how our F-stat is actually constructed, which is the mean square model divided by the mean squared error. And so if there actually was an association, then we would expect that our fitted values from our regression model would tend to be pretty different than the mean response value. And so that would tell us that our model is actually kind of providing something more than if we had just used like the simple mean of driving distance. And so because of that, that would mean that large F-stats are going to be more evidence for our alternative hypothesis that there is an association. And so the answer to this would just be large because the mean square model would be large, at least relative to mean squared error. Since fitted values from our line would be different than just the overall mean. Another way that you could think about it is that if the fitted values were pretty much the same as the overall mean, then why would we need our regression model in the first place? We could just use the overall mean, and there wouldn't really be any evidence for an association between driving distance and driving accuracy, or in general, a predictor and a response. So all of this can be expressed in this ANOVA table, which you may or may not have seen in IntroStat at all. But either way, we'll draw it here. And so this table is just meant as like a way to helpfully organize all of the other definitions that we've already talked about. So there's been a lot that we talked about, right? We talked about the mean squares, the sum of squares, the degrees of freedom. This table is meant to be a way to organize those to make it easier to think about them a little bit conceptually. And so in this table, we're going to have a column for the source, which is going to be our three different sources, so model, error, and total. We're going to have a column for sum of squares. And so we defined those earlier, where the sum of squares model was the fitted responses minus the overall mean squared. Sum of squared error was the observed responses minus the fitted responses based on our model. And sum of squares total was the observed responses minus the overall mean squared, adding all those up. And then there will be a column for our degrees of freedom so that we could kind of organize those. We already said that degrees of freedom for model in the simple linear regression case is 1 because there's two parameters, the intercept and the slope. Degrees of freedom for error in simple linear regression are always going to be n minus 2. We're only writing this extra again because when we transition to multiple regression, it'll hopefully make the transition a bit easier when we're thinking a bit more generally that we might have more than one predictor, and that would affect the number of parameters in our model. Degrees of freedom for total are n minus 1. And then we talked about mean squares. And so mean squares are what ends up getting used in our f-stat equation. And so mean square model is going to be the sum of squares model divided by the degrees of freedom for model. And so it's going to be this divided by 1. Mean square error is sum of squares error divided by degrees of freedom for error. So this quantity that you could calculate by hand, but we never actually will, divided by n minus 2. We said by convention, mean square total isn't reported. The only reason it's not reported is that it never gets used in anything, so it just kind of gets left out. Then there will be a column for your f-stat. And we defined our f-stat just super recently as mean square model divided by mean square error. And then the last thing will be a column for our p-value. And so this will be our p-value for the hypothesis test with the alternative hypothesis that there is an association. And so our p-value, we'll write over here, is a shaded area of the F distribution to the right of our F statistic. So why to the right of the F stat? That's because we agreed in the previous question that large F stats would indicate that there is an association. And if you remember from stat 113, the p-value is the probability of getting data that's kind of more in agreement with our alternative hypothesis than what we actually observed. So more in agreement that there is an association would mean that that f-stat would be to the right. In R, you'll get more practice with this in the R section for this, but you could use this pf function to get the p-value, and we need the 1 minus part because R always calculates areas to the left of the statistic that we put in, so area to the left of that f-stat, when we actually want the area to the right. Okay, so this video, as well as the last one, were both, I guess, a bit conceptual and a bit theoretical about this overall f-test. But if it doesn't really make complete sense now and it's not clicking, I think it'll be really helpful to kind of go through these examples, see this ANOVA f-test in R, and so you'll get some more practice that way, and then see what this ANOVA table looks like in our golf example, so you'll get a second example of practice with a practical data set that I think will help make sense of the different components. As always, definitely let me know if you have any questions, and we will pick up with some confidence intervals and some prediction intervals next.